All right, good afternoon. Thank you so much for joining us today for this week's session of the Parks College weekly webinar series. My name is Amy Price, and I'm the outreach coordinator here at SLU's Parks College. I'll be joined today virtually by Dr. Mitchell and Dr. Ebel, who will be sharing information with us about robotics at SLU. We are very excited to have you joining us today from wherever you are. Thank you for taking the time to virtually visit us and learn more about the aviation and engineering programs at St. Louis University. In total, Parks College has programs available in aerospace, biomedical, civil, computer, electrical, and mechanical engineering, as well as flight science and aviation management and physics. We hope that you'll hear or see something today that piques your interest. Throughout the webinar, we encourage you to submit any questions you may have to the Q&A feature at the bottom of your screen if you're viewing through Zoom, or in the comment section if you're viewing through Facebook Live. We'll do our best to answer as many questions as possible during the last few minutes of our session. Throughout this webinar, you don't need to worry about turning off your microphone or camera. You can hear and see our presenters throughout the webinar, but we cannot hear or see you. This session will be recorded and posted to our YouTube page in the next few days, and you'll receive an email with that link when it becomes available. If you would like to view any of our previous webinars, you'll also find those recordings in a Fall 2020 playlist and a Spring 2021 playlist on our YouTube page. So now, with that introduction out of the way, I am now happy to introduce robotics at SLU, and Dr. Mitchell, I will let you take over from here.
Thank you, Amy. So like Amy said, we're going to talk about robotics. We're going to spend a little bit of time talking about what you study in robotics as a college student. And then we're going to lead you through just a discussion of several of the robotic projects and experiments that are going on here at SLU. So when you study robotics, robotics is typically a cross-disciplinary degree shared by four main disciplines, that being electrical engineering, computer engineering, mechanical engineering, and computer science. As an undergraduate student, you typically have to pick one of these to be your home department, and then you would pick to take some of the things that live in the other departments, but you primarily look at just the stuff in one of the departments and a little bit from the others. So I've separated out the kind of main things that people study here at SLU in the area of robotics between those four disciplines. So under electrical engineering, we do a lot of things with how to perceive the world. So in sensor and image processing, these are kind of the same thing. It's just that a camera is such a big data sensor that we separate it apart. But in sensor and image processing, the idea is to take the electric signals that come out of different sensors and different cameras and try and make it so that the robot has some idea of what's happening in that sensor or image. So, you know, is it looking at a chair, or is it 6 inches away from a wall, or is it about to fall downstairs? So trying to make those decisions. We also deal a lot with the electronics and the power that are on the robots. So robots are all about batteries and motors. The electronics that go between the batteries and motors are designed by electrical engineers in nature. In computer engineering, we deal with the computers that are on robots. All robots are controlled by some type of computing element. So we deal a lot with how do you build those computers? How do you select the processing elements? How do you program those computers? We do some stuff with actually designing custom hardware. And then we deal with how do you make your custom hardware and your software talk to each other and collaborate with each other. In both electrical and computer engineering, we deal a lot with teaching how to do things with mobile robots. So in the computer engineering version of that, we teach you how to mathematically describe a robot and how to move it around under that mathematical description. In the electrical engineering version, we teach you how to use those sensor and image processing techniques to make your robot move around on its own. So how do you make it see walls and see features and avoid things? Mechanical engineering has a lot to do with mechanical design. So mechanical design is how do we design hands and elbows? How do we make wheels? So all that stuff that you guys are used to with robotics, how do you make a robot actually look like a robot and move like a robot? And then mechatronics. So after you've made your robot look like a robot, how do you use motors and other actuators to give it motion? In computer science, we study things like artificial intelligence, computer vision, and motion planning. So how do we make our robots do things on their own? And how do we make them be able to move around in the environment and do things like find a door and open it? So you can see that all of these different pieces come into play when you're building a robotic system. But unfortunately, you have to pick a few of them to study. That the area is just too big to know everything. So I'm going to let Dr. Ebel talk to you a little bit about what we do through the curriculums in electrical and computer engineering. This particular slide is demonstrating what some of our freshmen do with robots.
Yeah, so our freshmen, we give experiences in robotic ideas at a very early stage in our curriculum. So this is our part of our introductory course into electrical engineering and computer engineering. And what you're seeing on the left here is a control algorithm in the far left, a control algorithm that is not precisely tuned. And the robot will tend to meander from side to side. What you're seeing in the middle is a very tightly controlled robot. And if you look at the front on the bottom, you'll notice these 5 red blocks there. Those are electro-optic sensors that, well, actually they're infrared sensors, I believe, that are detecting the degree of overlap on the black line that overlays the white background. So the middle robot is a well-tuned robot that is tracking extremely precisely. And in the far right, you see the robot that is well-tuned trying to navigate turns, and it performs very well on turns with a broader radius, and it has some issues with tighter turns, which means that there are probably some additional tuning that could take place for that. But in our both of our programs, at various stages throughout the curriculum, you're exposed to robotic concepts, both in our freshman class, in some of our junior level classes, especially junior design, and in a number of our elective classes that were sort of previously listed under the topics for the various degree programs.
So now we're going to spend some time talking about some of the different projects that go on here at SLU in the area of robotics. A lot of these will have to do with things coming out of the electrical engineering or computer engineering disciplines. Some of them will come from other places. So the board on the screen here is an infrared camera. There's nothing really special about an infrared camera, but what's special about this infrared camera is this board was designed to be part of a spacecraft. So you've seen in previous episodes, if you've been following along, that we have a space program that designs satellites. What you may not have seen is that we actually design the electronics that go inside those satellites. So this is a good example of what some of the computer engineers have done with some of their extracurricular activities. This particular board, so an interesting note about trying to do things in space is doing things in space requires you get there, and getting there is almost as hard as being there. This board was on top of a rocket that was launched out of California and unfortunately is in the bottom of the Pacific Ocean right now. So if you want to know some real interesting bad stories about being in the space industry, we have some we can tell you. This is another system we put together. So we put this together in conjunction with a lab that deals with drones and other autonomous flight vehicles here on campus. The people from St. Louis University's meteorology department came to us and said they had a need to take weather balloon sensors. So that box on top of this craft is the sensor that would normally be on the bottom of a weather balloon, and use those to collect data more than once a day and at lower altitudes than weather balloons operate at. So we helped put together a craft that we could fly. We flew this 4 or 5 times a day for a couple of weeks to demonstrate proof of concept. Um, and we made, we were able to reuse this sensor. Typically, this sensor is kind of a one-time use thing, because you launch a weather balloon from St. Louis and it may land off the coast of Florida. You have no idea where that balloon's going to go, because it's completely dependent upon where the wind blows. This particular sensor was nice because we could sample air at the same point repeatedly throughout the day and week. In our department, we do a lot of stuff with putting technology into the education. So this is a robotic arm that we are developing a web tool to make it so that students can interact with this online. The hope being that we'll be able to develop something where students can experience how to program, configure, and otherwise operate an industrial style fixed arm robot um, remotely. So rather than having to go to where this arm is and interact with it one-on-one and be on the SLU campus, and we were doing this long before the COVID thing forced all of us into a virtual mode. We really want this to be something that we can turn loose with middle school and high school students, and other people throughout the country and world can come and experience, what it's like to try to both program a stationary arm, but also operate a robot remotely. When you only have a single camera and a single point of view trying to tell you what your robot's doing, perspective gets to be really difficult. And that's something that, as we progress forward in technology and we enter this area of operation where a lot of things are going to be teleoperated, that's going to become something really important. So we're putting this together not only as a teaching tool for what we call forward and inverse kinematics of figuring out what your robotic arm's doing, but how do you experience something like that in an environment where you can't touch it and you can't look at it sideways, and you just have to rely on what you can see. Our students participate in a number of robot competitions. So in the electrical and computer engineering departments, we have a competition put on by our National Professional Society, the IEEE, where we build 1 foot by 1 foot cube robots to perform an autonomous task. Those tasks change every year. In the aerospace department, they build flying vehicles, autonomous flying vehicles, to do similar things. So AUVSI is another national organization. This time it's of autonomous vehicles. These craft typically have to go into a field, find something, and report back something about it. Frequently that something is an injured person, and they have to report back the status of the injured person, or maybe they have to deliver a tracker to where the injured person is, or maybe deliver food and water. There's a number of ways they modify this, but it's all done from an aircraft that you just set down on the line, push the button, and walk away from, and it has to go do its own thing. You'll notice a theme here around these collegiate projects that's a little bit different than the projects that are done at high school level, and that is this level of complete autonomy. And that's one of the things that you're gonna learn as you go through the computer science, computer engineering, electrical engineering portion of robotics, is how to give robots that level of autonomy where you can push a button and turn them loose and have some trust that they're going to go do what you ask them to do. A lot of the work that we do is in making robots safer and making them more useful. So this is another flying craft, but this particular craft, if you look closely at it, there's little red squares and gray wires in places that you wouldn't normally see them on a drone. So this drone has been outfitted so that we can measure what's called its vibration performance. So what we want to measure is how it shakes. Because if you damage a structure, they shake differently. So any of you that have flown a drone know that if you damage the propeller, the drone makes a strange noise because the propeller flutters. Well, that fluttering of the propeller makes the whole craft shake at that frequency. But if you damage any part of the substantial structure of this craft, the whole craft will shake a little bit differently. And by measuring that, we can characterize that damage. And if we know what the damage is, we can program the autopilots to recognize that damage has occurred and do something differently. So a lot of the work that the aerospace people are doing, we're measuring data for them and getting them craft that they can do this vibrational analysis on. They're taking that data and building smarter autopilots. So the aerospace people working on these drones, they're figuring out ways so that if they detect that a particular propeller has been damaged enough, they can turn that motor off so that it quits shaking the craft and then still put the craft on the ground in a controlled fashion. In other words, we can damage these crafts and they do not fall out of the sky like you've seen a lot of drones do. You want to talk about our summer camp, Will?
Sure. We offer a summer camp, a robotic summer camp here at the university in Parks College. The last summer, that camp was entirely virtual, and I believe this summer it is going to be entirely virtual too. So what we have students do is building a mobile robot like the one you see here, and it has an Arduino processor on the top, a processor board, I should say, and a motor shield that lies on top of that. And below, although we can't see it, there are some line following sensors, sort of similar to the ones, well, not similar, but functionally similar to the ones that you saw in the videos earlier on in this presentation. And what the robot needs to do is it needs to navigate a course, and that course involves lines on paper. But the lines also contain symbols, and the symbols have to be detected, and they will tell the robot which direction it needs to turn when it comes to a fork. And the goal is to get the robot to start at some place and end up at some other place, and to correctly read the symbols and to be able to track the lines well. We go through a lot of the specific algorithms. We talk about concepts involving programming, how you represent data in the Arduino program, and how you make use of that to achieve the functionality of the project that you're trying to achieve.
So you've seen that we build a lot of robots for use in classrooms and use on tables. We build robots for other purposes also. So this is a particular chassis that we've constructed. We've made use of it in a number of different ways. So there's a robot that hangs out in my lab that for 3 or 4 years gave tours of the building. He was built on top of this platform. This platform has been used so that we can teach pilots how to teleoperate things. So that same thing I talked about with the web-based robotic arm, where getting people used to being able to control systems they can't see and touch. We're not too far away from airplanes that are flown remotely, and getting pilots used to the idea that they're going to control an object that they can't see and touch. We use this particular robot for. We put it in first-person vision mode and let them teleoperate it. We basically locked them in a closet and said, drive this around the hallways. Right now, this robot's on loan to some people, to a senior design group that's using it as a starting point for developing an autonomous lawnmower. So something that we could just turn loose in the grass, tell it to stay within this box, and it would do something similar to what your Roomba does, except it'd do it for your grass outside. So we build these larger robots. We test them, or we use them for much bigger projects and a little bit more research type activity. There's a number of labs that you may or may not have seen in the previous videos that deal with robotics here at SLU. So this is our indoor flight cage lab. We have an indoor flight cage, we have an outdoor flight cage. We use both of these to do stuff around the designing of drones. So when you design a new drone, when you design a new autopilot, that first time you take it off, it may or may not do what you want it to do, and we have to be somewhat safe about it. So we put them inside these cages to let them fly around. The things we're studying are exactly what I talked about before. So how do we How do we study drones in such a way that we can determine that they've been damaged? And how do we build autopilots that can do things when they detect that damage? We also do some other more interesting things. So we're using Oculus Rift, which are VR goggles, to make it so that the people that are flying these drones, rather than staring at a computer screen that looks like an airport radar or something like that, they have a pair of Oculus Rift on so that they can actually see a virtual environment. We can project out, the data that the USGS and the NGA have about the landscape around where the drone is, so that the pilot actually has a realistic view of where the drone is flying. They can reach into the virtual environment and manipulate the drone, and the controls that you use with your hands are very configurable. So sometimes we just have them be drop-down box type things. Sometimes we actually have them be flight stick type things. But they're things that you just manipulate out in free space while you're playing in a virtual environment. But the cool thing is that it's not a video game where you're just playing something virtual. The craft that people control in our environment are actually in this cage flying around. We have a satellite lab that's a completely project-driven or completely student-driven project lab. So this is an extracurricular activity, completely undergraduate, student-driven. We get to the point where we can launch satellites about once every 4 years. Since I came to SLU in 2002, we've launched We've launched 3 satellites. 2 of them are in orbit and 1 of them is on the bottom of the Pacific Ocean. The satellites that we launched look a lot like this box towards the middle of the picture. So to give you an idea how big that box is about 6 inches square and about 1.5 feet tall. So that's the size satellites that we launch. But it's amazing how much student work and how much input from faculty it takes to get one of those put together in a way that it will work reliably unattended. So one of the difference about some of the robots that we deal with, especially the satellites, is that these robots, not only do they have to be autonomous, but we have to be able to put them in a box, ship them to California, let them sit on a shelf for 6 months, get on the end of a rocket and go to space, and then turn on and operate on their own. And we never get to touch them again. So these systems are built very differently. And the study and the testing that goes into these is pretty rigorous, because whether you're in space or you're building something to go inside the human body, or you're building something that'll be in some other dangerous environment, a deep cave, a nuclear power plant, there's a number of dangerous environments we build stuff for. You don't get to go touch and repair these things. They have to just work. And we teach students how to do that type of testing. Right. We have a lab called the Collaborative Haptics, Robotics and Mechatronics Lab. This is a collaboration between electrical students and mechanical faculty. This particular robot is a telepresence robot. If you're not familiar with telepresence robots, think about being in a Zoom session, only the camera and your display on the other end of the session get to move around, and you get to control where it moves around at. So if you want to get closer to the board, or you want to turn to look left, you're in complete control of your camera and display. Some of these to get to be relatively complex. One of the things that they study in the Chrome lab is how do you make telepresence robots seem more acceptable. So if you just saw one of these sitting in the corner, you wouldn't think that there's actually a person watching the world and interacting with the world from there. But it turns out that if you just give them an arm and teach them how to shake your hand when you walk up to it, that's about all it really takes for somebody to understand that there's actually a real person on the other side of that robot. It doesn't really need to look like a robot. It just needs to do a few things that you're used to doing, and people are much more accepting of these things. Some of the other stuff that we do in telepresence is, or not in telepresence, but in the Chrome lab, is we figure out how to make technology more accessible to the visually impaired, and how to use technology so that the visually impaired can interact with the world better. All right, and the last lab I want to talk about is the biomedical engineering people have a robot that they're teaching to perform surgery. So there's a lot of robots out in the medical industry right now where the doctor holds onto a joystick and the robot is kind of a extension of their hand and arm. That's not what they're doing with this robot. This robot, you put a patient inside of a live X-ray or MRI machine. This robot watches the live medical imagery and actually conducts surgery without intervention from the doctor. So this is a fully autonomous surgical robot. Right now, the surgery they're trying to get to is the placing of pins. So if you have a broken bone, this robot can put a pin in your bone more accurately than a doctor can. The doctor kind of tells the robot where it needs to go, and then the robot puts it right there. I thank you for your time. I think Amy is going to ask us a few questions on your behalf at this point.
All right. Thank you both, Dr. Mitchell and Dr. Ebel. Dr. Mitchell, if you wouldn't mind closing that presentation, we'll get
There we go.
all of our faces on screen. Okay. So if anybody has any questions, feel free to put those in either the Q&A feature in Zoom or the comment section if you are on Facebook. But I'm going to get us started because you know, based on your presentation and just from what I know that goes around parks, there's so much opportunity for collaboration when it comes to robotics. So you mentioned, you know, applications within meteorology, within aerospace engineering, our aviation programs, and then the medical field. So what, you know, when students come into the program, do they need to have that kind of mindset already in place, or are there research projects that they can just get involved in if they go, you know, maybe they're more medically leaning, maybe they're more aviation leaning, just as a track for students who come into the program? What does that look like and how do they get involved?
So we try to support both of those ideas. We've had students that come in the door and have a very focused intent on where they want to be and end up. And those people get supported through custom projects, through the fact that we have open spaces for student projects. Several of them have gone on to start businesses around the projects they bring in once they leave SLU. So that is one thing you can do. You can show up with something that you are really wanting to do. Now, if it's a great big thing you really want to do, we might have to talk about how we fund it. But then there's also a lot of these projects that people that are just working on around the community. And what I frequently tell incoming students is ask people what's going on. Go talk to a lot of people, but find something that you're interested in, and it can change in your 4 years here. You know, if you find 3 months into working with Dr. Hall on medical surgery that you're not really interested in that, go find something else. You know, I talked about 10 or 15 of them here. This is just a small sampling of what's going on.
I love that. Thank you. For our high school students, I know we have the virtual robotics summer academy this year, which as a plug will be June 28th through July 2nd. And if you are interested in applying, we can still accept applications. So send us an email at parksevents@slu.edu. Right, that's my little plug. Dr. Ebel or Dr. Mitchell, do you have advice for high school students now who you know, think that they want a career in robotics? What can they do now that they're in high school before college?
I would say, first of all, there are at many high schools, you do have some sort of robotic type activities that are going on. It could be the first robotics competition, or maybe something local to your area that's that is robotic related. One big thing I would say is get involved in anything you can outside of your curriculum, outside of the courses that you're taking that relates to robotics, and there are usually things you will find. In terms of coursework that you can take, programming is always an important aspect of robotics, because without the programming, the robot has no intelligence and can't really do anything. The second thing I would say is mathematics courses. You don't have to be a whiz at mathematics, but mathematics does form the foundation for the engineering programs that students participate in here, and it's something that that you do need to involve yourself in to some degree. Those are probably the major things. Dr. Mitchell, do you have anything else?
I think you covered most of them. I would reinforce, find something you can do that is mechatronics in nature if it really interests you. And by that, I mean something where you can write some software and watch that software control something physical, whether it be spin a motor, ring a doorbell, and just build from there. If your high school doesn't have a robot team or robot club, you can get involved with some of this stuff for 30 or 40 bucks to start with. I mean, it's not an expensive thing to put your toe in the water and see if it's something that you could build a career out of.
All right, and last question for each of you. What's the future of robotics? Where are we headed? Is it autonomous systems everywhere? What's that look like?
I think technically we are just ending what is referred to as the information age, which culminated in the cell phone, which took 50, 60, 70 years to bring us to. And we are really entering the robotic age, I would say. I mean, I think there's a lot of scientists and engineers that feel that, yeah, robotics are going to become a more and more important part of our future. The day will come when you probably will not drive the car yourself. A car will drive itself. A car will drive you around. You'll just give it a waypoint, drive home, and it'll just do that. And you can sit back and work on your computer or whatever the case may be. Robotic surgery was something that Dr. Mitchell brought up. I think you're going to delivering packages to the home using robotic drones. I think you're going to see robotics become a critical infrastructure piece of the entire world and the way it operates.
So we've had robots in the industry for a long time. They've been building our cars, but with this advent of big data, we're seeing robots get enough intelligence to leave the factory and come do other things to help us. And the two of those, I think, are going to form the next 50 years of evolution of science and industry. Coupling this idea of we can process very large data sets very quickly with we can use the results of that processing to manipulate the world through robotics is really where we're headed next.
That all sounds very exciting and totally over my head, but I know we're going to have some great engineers coming up and through our program in years to come. So I want to send a big thank you to Dr. Mitchell and Dr. Ebel for sharing your time with us today. And a thank you also to our viewers for joining us. We hope that you did enjoy this virtual visit to learn about robotics at SLU. If you would like to learn more about our engineering programs at the university, please visit slu.edu/parks. And also plan to join us in this space again next week for a webinar about computational fluid dynamics and our aerospace engineering program at Parks College. That will be Thursday, April 15th at 11:30 a.m. And this concludes our webinar for today. Thank you again and have a great rest of your evening.